Hi, I'm Christina, and I'm going to present to you our tool demo paper, GraphifyEvolution, a modular approach to analyzing source code histories. So far for code smell evolution analysis in mobile applications, Hecht et al. Analyzed 100 specific code smells using Paprika. They applied Paprika to different versions of the same applications and used this to track the quality of mobile applications over time. Tufan et al. Implemented a tool called History Miner that runs the core on change files on the change files in each commit. It outputs a list of commits for each file where this file was changed and if it had any code smells. Habshi et al. Implemented Sniffer, a tool that extracts commits, detects code smells using Paprika, and outputs the code smell evolution of a project. All these tools output the information on code smells for each commit, but we felt like it might be more useful to have more information on the structure of the application and to be able to add additional analyzers and their analysis output to the structure of the applications. So we implemented a modular solution that can combine a lot of different analyzers. This tool is called GraphifyEvolution. It can analyze either a lot of applications, one application, the evolution of the application, or a single version of application. It is possible to add analysis results from different external analyzers, for example, Insider, jscpd, and it is very easy to add additional external analyzers. GraphifyEvolution analyzes the application, enters its data that includes structure, smells, history, and some additional information that could come from external analysis into a Neo4j database. Then developers can query the Neo4j database to answer possible research questions and analyze them in whatever software they like. GraphifyEvolution is built in a modular way. There are 5 components that can be implemented and where the application can be developed further. When GraphifyEvolution is run, then first of all, the path of the application has to be provided. Then one has to say which language the application is written in. Currently, Swift, C++, and Java are supported, but additional languages can be added if the syntax analyzer interface is implemented. It is possible to either analyze the evolution of an application or not the evolution of the application. If the evolution flag is present, then the Git app manager is used. Otherwise, a simple app manager that creates an application manager for the given path is used. If the bulk JSON path argument is provided, then bulk analysis of multiple applications is done. It is possible to provide either none or multiple external analyzers. Those analysis results are then also entered into the database. External analysis can be run on a class basis, which means that in this case they are only run for classes that were changed in this application version, or they can be run on application basis, which would mean that they are run for each app version. GraphifyEvolution enters everything into the Neo4j database that is a graph database. In this graph database, we then have different nodes. One of them is an app node that represents different app versions. App nodes are connected to class nodes. Class nodes are connected to method and variable nodes. Method nodes can be connected to variable nodes by the uses relationship or to other method nodes by the calls relationship. Additionally, to show the evolution of the project, the change to relationship shows how the app versions, classes, variables, and methods have been changed. As a small example to demonstrate the database structure, we here have a house class with a variable doors and method close doors. This class application is changed by adding an additional class and by changing the method close doors and the variable doors. Then an additional method is added to the door class. The closed doors method is changed, and we can see that if some nodes are not changed, for example, the doors and these closed variables, then they belong to multiple versions of the same class. This makes it possible to only add the needed information into the database and add new nodes only if something has really been changed. For the preliminary evaluation, we analyzed 30 open source Swift applications that included 3,878 different app versions. And we chose three simple but interesting questions that could be answered by querying this database that was populated by Graphify Swift. First of all, how did the number of long methods evolve in Tweetometer app? We chose this app as this application had a lot of long methods, and we chose the long method smell as this is a simple smell to understand. By querying all methods in applications named Tweetometer that are long methods, we can find the count of long methods for each app version. And when we plot this number, we see that over time, since the number of app versions grows, we see that over time the number of long methods first grows and then suddenly drops. So probably at that point, application was refactored. The second question, did methods become too long over time? We can query long methods and see how long the chain of change methods before this method was, providing that none of the methods in this chain were long methods. We see that there were 158 unique long method instances, and 131 of them were long when they were added, and others were others became either long after 1, 2, or more changes. This is an interesting question to ask, as previous research has mostly shown that code smells are introduced when the code is introduced into the repository. But we can see that there are also long methods that actually became long during the development. And as a third question, we ask if we can find commits that removed vulnerabilities from code. Vulnerabilities were added into the database by the insider external analyzer, and we can find first all the vulnerabilities, and then we'll find classes that the vulnerable class was changed into that didn't have any more vulnerabilities. And we found that vulnerabilities were removed in 3 applications and in 5 different commits. For future work, we plan to improve Java and C++ support, to add additional support for dependency managers, to improve the performance of the tool, and to create a public database of analyzed open source with libraries. This would make it possible to, when analyzing the IONOS application, to directly connect it into these already analyzed libraries and to see if maybe there have been vulnerabilities introduced through third-party dependencies. And current ongoing and future research, we are planning to do a large-scale study on code smell evolution in iOS applications to analyze the evolution of vulnerabilities and possible connection to code smells, and to analyze the vulnerabilities introduced to third-party dependencies.